Okay, in this video we need to talk about the last section in Unit 5, and that's going to be electron configuration and periodic properties, really, or patterns, is kind of what we're going to be talking about in this section. Alright, now the other term that we do for patterns is trends. And even if you think about the word trend, it's usually a pattern, right? Everybody follows the same idea, and that's what we're going to talk about with trends. And there are certain patterns or trends for the periodic table. It's why it's organized that way. And for each trend, there's certain things you should know. You should know the definition. What does it mean? We've already done most of these with our vocab. Number two, what is the trend for the period in the group? And that just means, does it go up, or does it go down, or does it increase or decrease as you go across a period and then down a group? Because periods are the horizontal sections, groups are the vertical. And then you also need to know why. The good news is that the pattern, the actual trend, and the reason why, a lot of them overlap. So a lot of time it's just making that same connection. Alright, so let's talk about atomic radii. We've talked about this before. Radii is plural, radius is singular. But the actual definition that we use for radii, because it's the better one, is half the distance between the nuclei of identical atoms that are bonded together. So if you have two chlorine atoms that are bonded together, the entire distance between them is 198 picometers, which would be 10 to the 12th, just as a reminder. 10 to the 12th meters. And that comes out to 99 picometers. So that's how we figure out atomic radius. Now, with atomic radii, the pattern is this, is that across a period, as you go from left to right, the size decreases. Well, what happens is there's an increased number of protons in the nucleus, attracting the electrons that are all at the same level. And I'll try to illustrate this a little bit better the next time as well. But essentially, if I come down here and we go back to Bohr's simplified shell model, is that when we're adding, let's say, in the second main energy level, okay, if this is n equals 1, this is n equals 2, every time we add another electron in that second main energy level, 1, 2, 3, 4, 5, 6, 7, we keep adding those protons in the middle. And they're being added at the same distance. So every time you add a proton, it can pull all those electrons in just a little bit closer. Now, for the group trend, it increases size as you move down the group. Why? Well, you keep adding energy levels. Even though we know it's not as simplified as this planetary model, and we'll update the quantum model, you have them being added to the atom in order to increase the atomic radius. And that's all this pattern is showing here. It says the atomic radius increases as you move down this way, and it decreases as you go this way. And that's what that trend shows you. If you look at group, or the second period, you start with lithium, which is 152, right? And as you move across, you get all the way down to neon, which is 69, and that's because for this particular period, every time you add another electron, this would be 2p, and this would be 2s, this would be 2p. You add more electrons at the same level, but you keep adding more and more protons, so that's why it goes down. And down here, you just keep adding shells, or you keep adding levels, so that's why it goes up that way. And this is just another chart to show you, again, that you see it increases as it goes down and it decreases as it goes across. Alright, so for example, if you had to rank magnesium, chlorine, sodium, and phosphorus according to atomic radius, this would be an example of how you have to apply it. If you go to a periodic table, they are all in the third horizontal group. And if we went from largest to smallest, all you have to do is be able to put them in order. So if the largest is over on the left-hand side, the first one that we're going to come to is sodium. Okay. Then the next one that we're going to come to is magnesium. Then we're still in that third period as you move across. The next one you're going to come to is phosphorus, and then finally chlorine. So you should be able to rank them as well, which really is just going to the periodic table and knowing the pattern. Alright, then we get to ions, and ions we've sort of talked about, but an ion is an atom or group of bonded atoms that have a positive or negative charge simply because they're gaining or losing those valence electrons that are in the outermost shell, and they're available to be lost, gained, or shared. And we've already seen these terms before, but a cation is positively charged because it loses an electron, and that will decrease the size of the atom because essentially if you give away an electron, all the protons that are left can pull the rest of them in that much closer. Alright, and just the opposite is going to happen with an anion. An anion, you get a negatively charged ion because it gains electrons. Now, we're not talking about changing the number of protons here, so it's still the same atom, but it's going to increase the size of the atom because now you have extra electrons that can help repel from the protons a little bit better, and so it's going to increase the size. Also, one other thing, ionization, which is one of your vocab words which we talked about, ionization, is simply the process of forming or becoming an ion. Okay, so that's all that you needed to put, which I think most people got before. Okay, now for ionic radii, the radius for a charged atom instead of a neutral atom. That's the only thing, which remember, it's the difference in the number of electrons, not protons. It's the exact same trend as atomic radii. Okay, so a lot of times the other thing that you'll see is if you have a blank periodic table, you should be able to draw that trend. And both atomic and ionic radii fall into the pattern where as you go down the chart, it increases. And as you go across the chart, it decreases. Now the good news, there's only one other pattern than that besides this. Everything else falls into the opposite category, and so usually by default we can figure that out pretty simply. Okay, ionization energy is the next one that is important. And for ionization energy, the definition, is an electron can be removed from an atom if enough energy is absorbed. So essentially, if you can take enough energy, you can take an electron away from an atom. And that's what our ionization energy is that the energy required to remove. You're going to see me do kind of an opposite here. And here is a general equation where A is simply a neutral atom, just a generic A for atom. If we add energy, we're going to rip off the electron and we're going to end up with a positively charged cation. Okay, we're not taking away any protons or neutrons, no nuclear changes here, but if we take off that electron, we're going to end up with a positively charged cation. So that's just a generic symbol for that. Now for ionization energy, as you go from left to right, the ionization energy increases, and that's because it takes more, it becomes harder to remove an electron and requires more energy. Well, here's that same reason. As you go from left to right, you have an increased number of protons attracting the electrons at that same sublevel or that same distance away from the nucleus. And again, I'll try to illustrate this better and explain it in class the next time that I see you. The group trend is going to be the opposite. It decreased ionization energy as you move down the chart. Well, why? It becomes easier to remove, the E stands for electron, and requires less, that should say, energy. Okay, due to the fact that those valence electrons are further away or farther away from the protons attracting them. So they just have the larger radius. Okay, and this just shows you some patterns. And there's a few more exceptions. You don't have to know them, but obviously if we think about it, the group 1s have one valence electron. They want to give that sucker away. So that's why they have with the exception of hydrogen. Hydrogen's always an exception. If you look here, lithium has the lowest ionization energy of anything across this period. Now there are some exceptions because you see boron jumps back down and then comes back up. Same thing with nitrogen and oxygen. It has to do with repulsions of electrons. We're not going to get into it this year. But the other thing is if you come all the way over here, here are noble gases, which remember, they're happy. They have all the electrons that they want, so it's going to take the most energy to rip away one of those electrons. So that's why for that second period, neon has the highest level. Again, just shows you increases as you go across, decreases as you go down. Alright, second and third ionization energies. This just simply refers to removing the second and third electrons. Okay, that's all that means. And it takes even more energy to remove a second electron than it does the first, so the second energy is always greater than the first. And then why? Well, after the first electron is removed, the Protons can hold on to the remaining electrons with more force, so it takes more energy to remove the next one and the next one and the next one. Just kind of the basics on that. Third will be greater than the second. Every time you move an electron, the remaining protons can pull what's left in, so it just makes it harder to rip away. And this just shows you another schematic, and the big take-home message here is that these are the group 1s, or the alkali metals. They have the lowest ionization energy because they want to give away that electron. And then up here you have your noble gases, because they are the least likely to want to give away electrons. And again, for ionization energy, it's going to be just the opposite. It's going to increase as you move across. It's going to decrease as you come down. Okay? Alright, then we get electron affinity. Electron affinity is kind of the opposite of ionization energy because this is the energy released when an electron is added. I always remember affinity has an A, so the electrons are being added. That's how I remember it. So it's going to be just the opposite. We still have our neutral atom. This time we're adding an electron, so we're forming an anion, and we're releasing energy. And because we're releasing energy, this would be considered to be exothermic. Okay, whereas ionization energy would have been endothermic because you were pulling the needed the energy for it to take place. Okay, the period trend, it becomes more beneficial to add an electron as you move from left to right. So the number increases, but I'm going to challenge your math here. When we say increases, we're going to say gets more negative, simply because it's an exothermic reaction. Why? Well, same why keeps coming up. You get this increased number of protons attracting the electrons at that level in the nucleus. Now for the group trend, this is as we go down the down the group, becomes less beneficial to add an electron, so it releases less energy. This whole idea of releasing energy is the fact that atoms want to have the lowest energy possible. So if it's less beneficial, it's not going to lower it as much. And when we say the number decreases, it's going to get less negative, and that's simply, again, because the electrons being added are further away from those protons. This is just a schematic that shows the highest levels over here, and then the lowest levels on the left-hand side. Okay, so again, and you guys don't have to know any of the exceptions this year, but it is going to increase as you go across, decrease as you go down. Exact same as what you saw with ionization energy. Okay, last one that we have is electronegativity. With electronegativity, it is a measure of how strongly an atom attracts electrons when it's in a compound. This only applies when an atom is in a compound because it's talking about their attraction to other electrons. And I always think of electronegativity as an electron tug of war. Okay, particularly we're going to talk about in the next unit about bonding. And with the tug of war, they're being shared. It's just how equally are they being shared. Fluorine is the most electronegative element. It's assigned a value of 4.0. It will always win the tug of war, and I refer back to this a lot this way throughout the year. And all others are determined by comparison. And this chart shows you all the numbers. You don't have to memorize them. You've got fluorine that's 4.0, and then you've got oxygen, which is next, and then nitrogen, and then chlorine is pretty high up there as well. But fluorine is the gold standard. Now for the Y, as you go across the period, it becomes more able to attract electrons. Well, there's that same reason, that increased number of protons attracting the electrons. So it's just got more force behind it in order to attract them. As you go down the group, it becomes less able to attract the electrons. Why? Well, because the electrons being added are further away from the attracting protons. And again, we keep seeing these same two ideas, and it's all about the attraction between the positively charged the positively charged protons in the nuclei, the negatively charged electrons, and how they are pulling each other towards each other, and how far apart they are, and how many there are. So again, we'll try to illustrate that. And last but not least, you've got that same trend that we drew for ionization energy as well as electron affinity, and that's going to be that it's going to increase as you go from left to right, and it's going to decrease as you go from top to bottom. Okay, I hope that helped.